Hello friends, this video on Structure of Atoms part 31 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 30. Shapes of atomic orbitals. If you see the wave function which you have gone psi has no physical meaning. So if you observe from a hi-fi microscope or something, you won't see the orbitals actually. This is something which you can't see because it doesn't have any physical meaning. It's just probability function, just a function. It's just a mathematical function for the coordinates of electron. However, for different orbitals, for a corresponding difference, wave function is function to r are different. The shape of orbital which you get from these wave functions as a function of r are different. And the square of this wave function gives the probability density for the electron at a given point. For example, for 1s, if you see, the electrons are there at this point. High probability of finding electrons. Right? It goes off and then from here there is no probability of finding electron. For 2s, if you see, it starts at this. Here it ends here. It starts here. There's a high probability here. Right? Again it dips off. That means this is the range where you get high probability of finding electron in 2s orbital. For 1s, this is the range where you get probability of finding electron. Correct? And we have regions where there is a zero probability of finding electrons, and they are called nodal surface or called simply nodes. So if you see in this case, I have my 1s, then I have 2s. So this is my 1s, this is my 2s. This is the region between 1s and 2s, and this is node because there you have zero probability of finding electron. For 3s also, if you see, this is 3s, the bigger circle, then I have 2s, then I have 1s. Then if you see, this 2 are the nodes where I have zero probability of finding electrons. Right? So nodal surface or node are the place where we have zero probability of finding or very less probability of finding electrons. Shapes of the atomic orbital, as I told, right, is just a mathematical function. It doesn't exist really, but if you want to understand this, we can draw a boundary surface diagram. Boundary surface diagram. Just example, in geography we have contour diagrams and latitude, longitude. These don't exist, right? If you go to any place, you won't be able to find latitude, longitude. It's just a convention we have used to make our life better. Similarly here also, these things doesn't exist. Black one you're seeing doesn't exist. They're just the diagrams which we create to make our life easy, to understand chemistry easily. So the boundary surface diagram of the constant probability density for a given orbitals give a fairly good representation of the shape of the orbitals. This just give you imaginative shape of the orbital. So in this representation, what we do, a boundary surface or a contour surface is drawn in the space for an orbital in which the value of probability density is constant. For example, in this case, at this point, the probability density is constant. So I'll draw one line. Here also it's constant. So I'll again draw one circle, but with the lighter color, because the color will decide the probability. And thus, if you keep drawing, you'll get something like this, right? Because if you see one dark here, the same darkness defines that the probability density is same to get the electron in this region. This is lighter, that means you have less probability of finding electron. Right? So in principle, if you see, there are so many boundary surface may be possible. So if you combine this, you get this kind of shape. Right? And generally we take the probability where it's 90%. 100% is not possible, right? Because if you say 100%, that means you are sure the electron exists there, and then it contradicts the Heisenberg principle where you say that you can't actually tell the position of the electron. So it can't be 100%, almost 90%. So we generally draw a contour and we get this kind of shape. Right? And boundary surface for a s orbital is actually a spherical in shape. For example, in this case, if you see, and this is a two-dimensional, it looks like a circle. In three-dimensional, it looks like sphere. Let's talk about the s orbital shape of the size of s orbitals. This is my s orbitals, and I'll show you the movement of electron also. All the s orbitals are spherically symmetric because they are all spherical shape. You see, this is how the electron moves in the sphere. If you see, this electron is going in, coming out. That's why you see the size is growing and sinking also. It's moving. So it's three-dimensional motion. The electron can be anywhere in the sphere, anywhere in this sphere, right? And that's what the orbital is all about. And please note, this orbital doesn't exist actually. This is just our visualization to understand this orbital in a better way. So the size of s orbitals increase with the value of n. So 1s has a small size, 2s bigger, 3s bigger, and 4s bigger. And pictorially, we see a radial node appears to be a spherical surface in which there is no electron density. If you see, the radial node I told is something where you don't have any electron density. The chances of finding probability is very less. The number of radial node is nothing but n minus l minus 1. So for s orbital, my l is 0. So for s orbital, the number of radial node is n minus 1. So if you see, for n is equal to 1, there is 0 radial node. For n is equal to 2, I have 1 radial node here. For n is equal to 3, I have 2 radial node here, right? Because for s orbital, l is equal to 0. So this becomes n minus 1. But this number of radial node n minus l minus 1 is a general formula for any kind of orbital. There's s, p, or d. The formula is same. And number of angular node is l. In our case, for s orbital, l is 0. There is no angular node. We'll discuss the angular node when we'll discuss the p orbitals. Just understand that there is a general formula. For radial node, the number is n minus l minus 1, a general formula. And for angular node, the formula is l, the number of radial nodes. Let's take the p orbitals. P orbitals look like this. You see, the electrons can move anywhere. There are 2 electrons in these p orbitals. If you see in the s orbitals, we had only 2 electrons. So there are 2 electrons can move anywhere. And it has 2 sections called lobes. So you see, there are 2 lobes actually on either side of the plane. And the probability of finding probability density is 0 on a plane where 2 lobes touch each other. This place also, there's a probability of finding 0 electron. And the size, shape of energy of 3 orbitals are same. The size, shape, and energy is same, but the orientation is different, right? The size, shape, anything is same. Energy is also same, but the orientation is different. And if you see, px, py, pz are 3 different way of noting this. So we'll continue with p orbitals. So like s orbitals, if you see, p orbitals also increase in size and energy with the increase in the quantum number n. That is 2p, 3p, 4p. The size and energy is more for this guy, 4p. Also, like as the probability density of the function for p orbitals also pass through a value 0, right? Besides a 0 at infinite distance, and those are called the nodes actually. The number of nodes here is given by n minus 2. Why? Because the general formula was n minus l minus 1. Here l is equal to 1, so this becomes n minus 2. So the nodes is n minus 2. And the radial node was L, the general formula. Here L is equal to 1. The radial node is 1. Right? Sorry, this is the radial node itself. So for 3p, this becomes 3 minus 2, 1. For 4p, this becomes 4 minus 2, that is 2. So the radial node formula here is n minus 2. But don't remember all this, just remember n minus l minus 1, the general formula. In this case, L is 1, so this becomes n minus 1 minus 1, this is n minus 2. So for 3p, my n is 3, so radial node is 1, 3 minus 2. For 4p, the radial node is 4 minus 2, it is 2, and so on. Angular node also is a planar or a conical surface in which there is no electron density. For p orbitals, we have one planar node. Why? Because for angular node, I told the number is L, and in this case, p orbital, the L value is 1. So it will have only one angular node. And since the energy E of each orbital is a function of only of n, right, then all n is equal to 2 orbitals have same energy. So if you say 2s, 2px, 2y, 2pz, they all have same energy for hydrogen. Right? But actually if you see 2s and 2p, they have different energy. That depends on n plus l for multi-electron. The number of radial node is given by n minus l minus 1. And if you see for p orbital l is equal to 1, so this becomes n minus 2. We have covered this here. And the number of angular nodes is given by L. So for p orbitals L is equal to 1. So the number of angular nodes is always 1. This is also covered. Let's take d orbital now. D orbital, you see it looks like this, and this also will have 2 electrons and they'll be moving in this orbital, right? For this L is equal to 2 and the minimum principal quantum number for this is 3. Why 3? Because for L is equal to 2, the minimum value of n has to be 3. Correct? Because L cannot be greater than n minus 1. There are 5 values of ml: minus 2, minus 1, 0, plus 2, plus 1. And that's why we have 5 different shapes for d orbitals. All the orbitals have equivalent energy, and all 3d orbitals, I'm telling. The d orbitals for which n is greater also have shape and shapes similar to 3d orbitals, but the energy and size is different. Shape is same, but the energy and size is different for orbitals which are greater than d. For example, 4d, 5d, they have same shape, but the energy and size is different. The radial node, besides the radial node, the probability density function for NP and ND are 0 at planes passing through nucleus, and they are called angular nodes, right? And for this, the angular node is L. For d orbitals, the value of L is 2, so there are 2 angular nodes. Now let's take the overview of atomic orbital. We have discussed the atomic orbital. Let's take the same picture once again and discuss things. So we have, in this case, we have, this is my 1s, this sphere is 2s, then I have 2p's, there are 2py, 2pz, and then I have 3s, and each of these will have 2 electrons. If you see all these moves, this is not moving because I have drawn this, so this 3s also will have 2 electrons which will somewhere moving around here and there, right? If you see, the black one moves only in this particular p orbital. The yellow one, if you see, moves only in the 2s orbitals. The green one here moves only in 1s orbitals, right? If you see, the red ones move only in this particular p orbital. And that's how it is. So we have different orbitals, and if you grow on, if you have one more 3s, if you have 3p, again we have to draw something like this here, the big ones. I can draw this. So it will be something like this. So this is 2, then I'll have something called 2px, 2py, and something like this. So it will be my p, right? So this is my p. This will be my 3p. And so on, it will be carrying on. It will have 3d also. Then I have to draw something like this. And all of this will start from origin actually. Correct? That's how the look and feel of this atom. Hope with this you get the clarity of how the atom looks like in the real world. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.